For the past 3 years, the industry has operated under a false premise that the main bottleneck to enterprise AI adoption is model capability. The models are highly capable. The actual barrier to scale is the human data interface. Complex organizations are structured around legacy code, dense compliance PDFs, and unwritten tribal knowledge. When we ask an AI to operate within this reality, we hit a cognitive constraint, not a technical one. The initial attempt to solve this involved throwing raw data into vast data lakes and letting the model sort it out. This produced an architecture entirely devoid of human legibility. Models extracted patterns and generated fluent answers, but the source knowledge was unauditable. The enterprise had no way to verify what the model actually knew, rendering the system ungovernable. The next iteration focused on retrieval, building RAG pipelines and internal wikis to feed specific documents to the AI. This improved accuracy, but introduced a new flaw: silent drift. An autonomous agent pulls a wiki page that hasn't been updated in 18 months. The wiki is technically accurate to the system, but factually wrong to the business. Nobody is alerted. This leaves enterprise AI deployments running what is known as the context lottery. Because the data environment is entirely unstructured, agents require more organizational context than any human operator can hold in their head. Sometimes the retrieval algorithm pulls the exact right operational context. Often it misses critical nuance. A business cannot scale operations on a lottery. Deploying AI safely requires moving beyond search and retrieval entirely. We have to construct a new cognitive architecture, one that structures organizational knowledge so machines can reliably consume it, and human operators can genuinely grasp it at the exact same time. During the early space race, NASA spent millions of dollars engineering a pen with pressurized ink cartridges that could write in zero gravity. It was an impressive feat of specialized engineering. The Soviets used a pencil. Today, the enterprise AI industry is racing to build incredibly complex context pipelines. We see elaborate vector databases, semantic routers, and re-rankers deployed to feed agents better data. This is the anti-gravity pen. It is sophisticated engineering that exclusively solves for machine consumption, completely ignoring the second half of the equation. Human operators must understand what an agent knows in order to guide it, challenge it, and make the judgment calls that models cannot. The missing component, the pencil, is a clean interface layer. Instead of over-engineering the back-end retrieval, the goal is to structure the context itself, making it intuitive and navigable for the person tasked with oversight. If the human cannot read the AI's operational map, they are removed from the loop. No amount of back-end pipeline sophistication can replace the accountability that a legible, shared interface provides. An organization cannot govern a data ecosystem that it cannot normalize. Currently, business logic is scattered across incompatible formats, some buried in code, some in legalese, and some in system configurations. Without a single language to bridge these silos, the enterprise has no way to audit what its agents are actually doing. Solving this requires a standard that compiles these disparate artifacts into a common structure, an executable operational runtime for business logic. We call this standard FOX, or Functional Organizational Knowledge. It functions as a translation layer that extracts pure operational meaning while stripping away the proprietary vocabulary of the source. For example, a 200-line Python script implementing a Python pricing rule is ingested by the FOX compiler. It discards the Python syntax to isolate the underlying commercial logic, producing a single structured skill node. A 4-page section of a GDPR compliance PDF undergoes the exact same transformation. The legal jargon is stripped away, leaving only the operational requirement for data erasure as a skill node that matches the pricing node in structure and clarity. Every resulting skill node contains 6 standardized fields: name, description, rationale, subskills, annotation type, and the responsible unit. This structure captures not just what the rule is, but the historical business decision behind it and the team accountable for it. By treating organizational knowledge as a compilation process, a business analyst can read and challenge a pricing rule originally written in Python without needing to learn the language. Simultaneously, an AI agent can query that exact same node without having to parse a legacy codebase. This universal language provides the mandatory bedrock for enterprise AI. It ensures that every agent and every human operator is looking at the exact same operational reality, regardless of where that data originated. Once you establish a universal compilation standard, individual skill nodes link together. They map dependencies, connect subskills, and assemble into a living, interconnected knowledge graph. This structure is the organizational digital twin. Most knowledge management systems rely on top-down intentional documentation, what the company claims it does. The twin is a bottom-up, self-discovered map. It charts what the systems actually encode and what the teams actually practice. This massive network graph represents the totality of the enterprise. But a map of infinite complexity is useless to an individual operator. It causes immediate cognitive overload. To make this twin functional, we rely on perspective architecture, a mechanism that renders the exact same underlying graph differently based on the user's role. When a compliance officer logs in, the graph dims. Only the specific branch of legal obligations, audit requirements, and regulatory nodes illuminates. She sees exactly the constraints her agents must respect, without the noise of unrelated configurations. A product manager logging into the exact same system sees a different configuration. The compliance requirements dim, and the customer-facing feature nodes and capability logic illuminates, providing a workspace tailored precisely to product strategy. And for an engineering lead, the view shifts again. The business nodes fade, isolating the API layers, platform integrations, and back-end configuration logic. Everyone navigates the same foundational reality. Perspective architecture eliminates organizational noise for the human, while maintaining the single, unbroken source of truth required for AI agents to operate accurately across domains. In traditional software design, when two different business domains interact, engineers build an anti-corruption layer, or ACL. This is a rigid, hard-coded boundary designed to prevent one domain's logic from bleeding into and corrupting another. The core flaw of static ACLs is time. Business domains evolve constantly. An ACL written 18 months ago remains static in the code, silently enforcing outdated logic. This causes hidden semantic corruption that domain managers cannot see. This architecture addresses drift by shifting toward human-authored semantic perspectives. Domain managers define the scope of their area through the map, allowing boundaries to be updated as the business evolves, without requiring an engineer to rewrite the underlying code. When an LLM agent accesses the twin to execute a task, it is entirely constrained by the perspective authored by that domain owner. The agent only reads the specific compliance, pricing, and process nodes designated as relevant. Because the system is dynamic, the LLM determines its exact traversal pathway at runtime. An agent handling a pricing exception takes a different route through the nodes than one handling a delivery escalation. It adapts immediately, but it cannot breach the authorized boundary. By making these boundaries visible in a mind map, they function as a shared, human-readable map. The domain manager who built the perspective can see the exact constraints governing their agents, closing the information gap between the human and the model. This creates a structural alignment we call fair play. Autonomous agents only execute within contextual boundaries that human operators can see, author, and actively audit. Every enterprise has a gap between its official documentation and its actual daily operations. We call this gap the drift. Rather than trying to hide this inconsistency, the twin continuously measures it. By matching intentional documents against self-discovered reality, the system generates a living governance signal, pinpointing exactly where knowledge is contested or where practice has abandoned formal policy. When you correct this drift using a change request, you update a specific Fox node. Because the logic is centralized, that correction instantly propagates to every single agent operating within that domain. Surgical remediation replaces scattered documentation updates. This brings us to the critical risk of deployment at scale. You cannot trust that every agent designer will correctly include every core compliance obligation in their system prompts. Relying on ad hoc prompt engineering to enforce enterprise rules is an unacceptable security vulnerability. The solution is the mandatory skill layer. This visual details the user prompt flow hitting a locked block. These are kernel-level rules, strict data privacy protocols, and core ethical constraints. They are structurally injected into the agent's context window the moment it enters a domain. Because this injection occurs at the architectural layer, no user prompt can override it, and no developer shortcut can bypass it. The rules apply uniformly, by default. True enterprise AI safety cannot be achieved by hoping humans write thorough instructions. It requires structural enforcement built into the bedrock of the system. The operational landscape of a modern business relies heavily on external SaaS vendors. When these vendors expose their capabilities via Model Context Protocol, or MCP endpoints, the Twin compiles them into native Fox nodes, placing them right alongside internal data. This means an LLM agent autonomously navigating the hierarchy discovers a third-party CRM capability using the exact same structural logic it uses to discover an internal HR policy. Vendor integrations become first-class, normalized organizational knowledge. When multiple enterprises adopt this same compilation standard on a shared platform, a network effect begins to emerge. Through an abstraction pipeline, customer nodes are stripped of proprietary configurations and identifiable data. What emerges from the funnel are clean, unbranded structural patterns for business logic. These patterns populate a shared practice library. Instead of drafting complex logic from a blank page, organizations can deploy proven, peer-tested architectural patterns. You begin with an industry-validated scaffold, vastly accelerating the implementation of reliable AI governance. This diagram shows the completed three-layer stack of enterprise AI. At the bottom, we have raw knowledge. At the top, we have AI agents and human operators. Wedged in the middle is a newly defined category, the Enterprise Context Hub. This hub ingests chaotic data from the base, normalizes it through the Fox standard, governs it via perspective architecture, and serves structured context tailored for machine consumption and human comprehension. Artificial intelligence will inevitably process vastly more data than human teams can cognitively hold. That volume gap is a permanent feature of the technology. The goal of enterprise architecture is not to constrain the AI's capability to human limits. The goal is to build an interface robust enough to keep human judgment meaningful. Organizations that build this interface secure a lasting operational advantage. They allow their AI models to function at maximum scale, while ensuring their human operators retain clear, verifiable control over the decisions that actually matter.